More cowbell, please. More cowbell. Thank you. All right. So this talk, my name is Josh Pitts. I'm the core author behind Backdoor Factory and BDF Proxy. If you don't know what that is, it's code. Hey, what's up? It's code that patches code into other people's code, compile code. So yeah. All right. So why this talk? Well, if you do any iOS or OS X forensics, if you use code signing as part of your forensic workflow, if you're not really sure how code signing works, or if you want to hide data from forensics folks that don't know how code signing works. Got it? All right. So some ground rules. Everything is post-install. There is no direct malicious execution during this talk. There is some malicious execution, but it's post-install. And see, if you really want to see some gatekeeper bypasses, go see Patrick Wardle's talk. So if you do this on Windows, you append data to the end of the binary, it's no longer signed, as expected. If you do this on OS X iOS, it still is, sort of. It depends on how you check. It depends on if you can check correctly. Yeah, so I took this bug, and what I thought was a bug, and a resource issue, reported it to Apple in April. In June, I was given a CVE for the resource issue, but I noticed that the adding data to the binary still was, that issue, what I thought was the issue, still existed. El Capitan came out September 30th. Issue still existed, so I reported it to Apple again. I talked with Apple engineers on the phone, and I got their official response. Use only strict checking. And who, just a show of hands, anyone know what that is? There's like maybe 1, 2 hands. There's one works for Apple. So let's go into it. So strict versus no strict. So I drew this on a napkin for you. You see the color? Okay. So strict checking, think of it as gatekeeper. Gatekeeper, what it does, at least from strict checking standpoint, verifies the integrity of the file. If there's an issue with the integrity, it will tell you the code signature is invalid. However, no strict checking it's only what is loaded into memory. If the binary is signed, that is checked. And so there's a definite gap there, right? And on iOS, there's only no strict checking. And I'm going to show you that. Okay? So, and this is a universal binary or a FAT file. Now, this has multiple architectures, and there's padding in between each architecture. These padding locations, they're not checked. So, I agree with Apple's assessment to use only strict checking. So I decided to look around in the industry and the tools that are available to see who's doing strict checking, where it's being taught. So here are the tools that, when I started this research, we're using just no strict checking. Now, OS X Collector is the reason it's off to the side from Knock Knock is because it uses code from Knock Knock. And then you have OS Query from Facebook, Google Santa. That's not really forensics, but I just threw it in there just so people know. Google Santa is a whitelisting tool, right? And so I was also told, I asked people who did forensics, who taught forensics, and I asked them how they would check code signing. And they told me this. This is not correct. This will just tell you if the binary itself has a signature and who signed it, but not if the signature is valid. That's a big difference. So really, unless you want to know who signed it, don't use it. I'm going to have an example of that here in a moment. But you do want to do strict checking. This is how you do it. There's many options. If you look at the source code for code sign, you'll see that there's a case statement, and all of these pretty much end up the same place. Now, this is how you do no strict. Basically, you do strict checking, and you throw the no strict check flag in. Now, you can't always use no strict, or strict checking. I'm going to show you that in a second. All right, so this is, I took LS, and I modified a binary in the signed envelope. So if you do code sign D triple V the binary, you'll see that it says it's signed by Apple. But if you actually do strict checking, you'll see it has an invalid signature, and that if you do no strict checking, it has an invalid signature. And that's what you want, right? This is what you, well, you don't want it, but this is how the check should fall out. Unfortunately, well, not unfortunately, but if you append data, I appended data to this binary, and you'll see if you do DVV that it says it's signed by Apple, right, because it's not checking. And then you'll see if you do a strict check that it fails strict validation, but if you do no strict, it's valid on disk. Okay? Now, if you see this, you have a problem. This is changing one single byte in the padding section between Mako binaries. There's no real way to know that that's the issue. You would have to open up a hex editor, be familiar with a Mako format, or use a tool that I'm going to talk about later on. And so if you have a binary like this, try to load it on OS X, Gatekeeper is going to say that it's damaged. All right, so going back to the FAT file stuff, I wrote something called lipocram. And what it does, it injects data into the padding sections. Because you can inject data into the padding sections and it doesn't break anything unless you're on iOS over certain size periods or sizes, but you can put as much as you want. And the binary still executes fine on OS X. So I wrote, so in this example, I have Firefox, right? It has two architectures, and I just cram ls into the FAT file, and it works fine. Now you may be saying, what if you're using a file carver like Scalpel or Foremost or something like that? Well, it's true. If there's no encryption, no anything, it'll find the magic header, and then it'll say, yes, I have this file here. But not if I do this. This is just taking OpenSSL, encrypting the file, removing the literal word salted from the magic header, and appending it to Firefox. And Firefox will execute fine, and it'll pass no strict validation. So you can also mess with the files on a iOS application and load them onto a non-jailbroken phone. So in this example, I take Chromecast, I copy it to a directory I created, and then I unzip it because an IPA is just a zip file. And then you'll see that I go to check strict check, and I can't do strict check. You can't do strict check on iOS binaries. It's just maybe the code sign tool is broken. However, you cannot do it. So, but you could do no strict checking, and it passes. Great. So I just go into the application directory. I append 2 gigs of data to the binary, random data, and then you'll see it's 2 gigs, right? I back out, and you'll see that the application is still no strict sign. This is the only way I can check it. And then I zip it up. You'll see there's still 2 gigs. And then I use Xcode to sideload it, but you can also use iTunes. Works fine with iTunes. So here's the before and after. Right? So it went from 28 megs to 2 gigs. So I mean, what can you put in 2 gigs, right? All right, so there are some limitations if you want the application to still work. If you go over a gig, the app instantly crashes. The information that the log puts out is kind of interesting. I don't have access to source code or decompiled the iOS kernel, so I can't tell you exactly the problem. But you're also limited to 15 kilobytes, about 15 kilobytes in the padding sections because you can't extend the padding. If you extend the padding, then the application will crash. And it's about 16 kilobytes, but I say 15 kilobytes so that you have some padding on either end of your data. So this only works. So you can put it on iOS 9 devices and all that stuff, but to get the data back off, it has to be iOS 8 or a jailbroken phone or below, right? The reason for that is that Apple has implemented app thinning. And app thinning, the easiest way to explain it is, let's say you try to, you're in iTunes, you're trying to transfer purchases. Instead of them coming from your phone, they come from Apple's cloud. And so you can't transfer the data back unless the phone is jailbroken. But on iOS 8, you can. Now, these techniques also work on unsigned binaries, such as the OS X kernel. Now, some people, well, there's SIP. But the problem with SIP is that if you haven't locked out recovery mode from a user can just boot in and disable SIP and then do whatever they want on the machine to any of the files on the machine. So if you're doing forensics, you can't depend on SIP to protect the files, so you can't count those files out, right? So we're going to take, and I just copy, I disable SIP, I copy the kernel locally, appended random data to it, and then I copy it back, reboot, and you'll see that the kernel's 1.2 gigabytes instead of being 10 megabytes. And there is potential for abuse. There's two files that I wrote. I haven't put them up yet, but hunchback.c and parse.c. What Hunchback does, it will take it can be a signed app, and then what you do is you append data that's been formatted with a magic header, payload size, then some shellcode. You append it to the binary, and then what it'll do when you execute it, it'll look to see if that data exists. If it's not there, it will execute normally. If it is there, it will execute the memory, take the payload, execute in memory, and then truncate itself so that it would pass strict checking. And then parse, all it does is look for binaries that have data appended to them, and then if it finds its magic header, then it will execute that data in memory. And then another potential for abuse that you've probably already recognized is data hiding. So there's potential for abuse if you do not know how to check code signing properly. You could be missing data that could be used for exfil, could be used for storage for exfil, or if someone wants to hide pictures, it could be for anything, right? So solutions. I wrote something called kyphosis, and that is the medical term for hunchback, because the original idea was you could take a 64 kilobyte file and have 5 to 6 gigs of data writing on it. So all this does is look at where data is not loaded into memory. If it finds something, if it finds extra data, then it says, all right, we're going to write this to disk for investigation. So it's Python 2.7, it's a class, so you can just import it into any projects that you're using. So this is an example where I changed just 1 byte in a padding section of Firefox, right? The one that gave the error. And this wrote this out the file so you can do like a hex dump on it just so you can see where it's been changed. Pretty straightforward. Now, I patched this into OS X Collector, which is a forensics tool that is developed by folks at Yelp. And what was kind of interesting is I ran this on my entire build. Excuse me. I ran this on my entire build. I have a pretty lean build, and I found that IDA 6.8 had a file, an uninstall file, that had extra data on it. And I thought I was owned, to be honest with you. But it turns out that it was a script, a legitimate script, that was packled is the new word, I just made it up. A TickleKit is packaged with TickleKit, and it was just, what happens is the binary would load, it would call this TickleKit, or tickle script from disk, and then load it into memory. So let's see, IDA 6.9 doesn't do this. I wonder why the change. IDA's not signed, so they didn't have to change it. But yeah, kind of weird. I submitted patches to the following repositories, and they accepted all the patches. And they were some of these patches were literally just 1 flag change. I mean, it was pretty simple, pretty straightforward. It just shows that, a lot of people don't understand how code signing works. And these are the differences. I thought there would be a performance hit. Really, it was faster to check strict than it was not to, to do no strict, because these are the flags. If you're going to use the API to call code signing, these are the flags you want to use. The first one you don't want to use. The middle one, at a minimum, you could just do strict checking. But if you want to check the last 3 there, if you want to check strict, if you want to check all the architectures in a FAT file, And if you want to check nested code, this is if they use the code sign tool to sign deep. So it actually, these ended up being faster than NoScript by a second. Kind of weird, right? Now OS X collector, same deal, ended up being 3 seconds faster. So yeah, in conclusion, run a little fast. You can stash data on Mako file formats and in the FAT file format. You really need to be doing strict checking where you can do it. But for example, on iOS, you can't do it. And then if you can't do strict checking, you need to run kyphosis against it or something else similar so that you can see if anything's been appended to it. And kind of a side note, PE and ELF files can be abused in the same way, except on PE it's pretty binary that the file is going to be signed or not. But on ELF there is no code signing. So you can append data to files also, and I really have not looked into the ELF file format. I have friends that know it really well, they could tell me. But there might be ways to hide data in the ELF file format. But who knows? Any questions? No? All right, thanks for your time.